How you doing? Clint Mason here, Kaizen Well Solutions. Today I'm going to talk about some basic optimization or a little bit about two-piece plunger system. When we get into this, try not to take too much time, but there's a couple of things to understand. A two-piece plunger system operates much differently than a conventional plunger system. A two-piece plunger is what I would call a velocity plunger. So when we're designing them, we base it on the well's gas velocity coming up the tubing, and I can pull this back to critical rate. A velocity plunger typically has all the energy it needs to surface a plunger and lift a fluid. It comes directly from the formation, unlike a conventional where we shut the well in and we build up that energy in the casing or annular area. Everything that comes into this well needs to push this, because we're really never shutting this well in. We want to keep this flowing as consistent and with as little off time as possible. So what is a two-piece plunger? Well, it's pretty simple. It'll have a sleeve, which you can see here, and a ball. And that's basically what a two-piece plunger is. But within that two-piece plunger, there's kind of two different styles. One is the Pacemaker style. And the Pacemaker style uses sleeve to ball weight ratio in order to keep the ball in the plunger when it's traveling. So that means we have to do some different, add a few extra things to our times and that to understand, and also to make sure that we have the proper weight ratio between the sleeve and ball. Now these work awesome, they're great. In fact, I prefer them over the other stuff we're going to talk about, as long as you get them set up properly. If you're running them with the incorrect ball and sleeve combination, you're going to have a lot of trouble, or could have a lot of trouble. So here's some basic rules for the basic weight ratio between a sleeve and a ball. It's basically 9-to-1. Now, it doesn't really matter. You don't have to go out there and grab a weigh scale and measure it and stuff like that. That's not what needs to happen. But basically, when you have a ball that's heavier, so let's say your weight ratio is only 5-to-1, the sleeve was only 5 times heavier than the ball, what that really means is that the ball will fall faster because of its area in the gas flow than the sleeve. And so if your weight ratios are off, what will happen is the plunger will be coming up, the ball falls out, and then before the sleeve can catch it, it'll have to travel all the way back down to bottom again, and then it'll catch it at the spring, and then it'll try to come back up again. So if you have this, you can always be less, so you could have the sleeve, say 12-to-1, which would even keep that ball and sleeve together even more. And basically what's interesting is if you take a two-piece plunger that's a Pacemaker style, and you put the ball and you put the sleeve into the lubricator, and you open up the well without it flowing, what you should hear happening is you'll hear the ball go ding, 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 it'll take off, and then the sleeve will take off once you get the valve wide open. And very quickly you'll hear it go ting, 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 and then it'll go clunk, and then you hear it fall like a conventional plunger. And it'll fall slowly. But if you hear it go clunk, and then it goes ting, 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 clunk, ting, 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 clunk, it means that the ball is basically so close in ratio to this 9-to-1 that it's not able to stay together. The sleeve falls at the same speed or slightly slower than the ball. So if you're doing that, anytime there's separation, it has to go down, hit the spring, reset, and come up. If you have the right ratio, though, that's ball, let's say it stalls for whatever reason, you have another plunger come on, which kind of bumps this well and it kind of stops flow for a second. Then if the ball happens to fall out, the sleeve just sits on top of it. The ball can't get away or can't fall faster than the sleeve. So it'll just stay together, and it always comes back. So that way it doesn't have to go all the way to bottom, reset, and come back up. So it might fall 50 meters or 150 feet, and then you bring the well back on, and it comes back up. So that's one of the key things about a Pacemaker style plunger, which doesn't have a retainer ring, doesn't have magnets, doesn't have any kind of little snap rings or anything in it. It's strictly a ratio of weight between the sleeve and ball. So here's some examples. So typically what you would have is like a 6-inch steel sleeve and a titanium ball, a 9-inch titanium sleeve and a titanium ball, maybe a 12-inch titanium sleeve and a stainless steel ball, a 9-inch steel or stainless sleeve with a steel or stainless ball, or a 12-inch steel sleeve with a tungsten carbide ball. Those would be pretty typically right around that, not the ratios that we would use, and that's, you know, give or take a little bit, but those are the typical combinations that I would put out there. Like I said, anytime, if the weaker the well is, so the closer you're getting to the minimum velocity you need to run this plunger, the greater you can increase that weight ratio. So I might use a 12-inch titanium sleeve with a titanium ball. Okay, well, that would give me a much higher weight ratio, so that means the ball just doesn't fall out as easy, and it can never really get ahead. The other thing is that this longer sleeve, the longer the sleeve, the more efficient it's going to use the gas that's flowing by it, i.e. it's going to create a better differential, it's going to move easier in the gas and all this sort of stuff. So it's actually going to be more efficient. So you can create a more efficient plunger that's going to work better. So even though when the well was strong, you initially started out, you might have been using a 9-inch sleeve and a titanium ball. But if you're starting to find that it's skipping and missing and stuff, the tendency people have is to go, well, let's go to a 6-inch titanium sleeve. Well, the fact is, what you should be doing is going to a 12-inch titanium sleeve with a titanium ball. You'll probably do better. It's the same thing. You might be running steel, but if you're getting down to where the plunger's not cycling as consistent, you want to go to a 12-inch titanium sleeve. You know, you might be able to do the stainless steel ball, but the longer sleeve is more efficient than the shorter sleeves will be. And of course, there's a 12-inch steel sleeve and tungsten carbide ball. When you're up into that, you're high volumes of fluid. And you got to remember, all of these plungers can fall at extremely high velocities. I mean, I've tracked a 9-inch titanium sleeve plunger. It fell, and now this was a low pressure, nice clean gas well, very little liquid in it, but I tracked it at almost 6,000 feet a minute. And in a well that's only, 8,000 feet deep, in less than a minute and a half, it's hammered into that bottom hole spring. And that's where the damage comes from in this type of system. It's, this ball and sleeve system, this sleeve can fall faster down than it ever will coming up. So you can really beat up stuff downhole if you're doing the wrong combination and if you're shutting in too long. Now, what happens if the weight ratio is incorrect? So the ball is too heavy. Say we got a tungsten carbide ball in a 9-inch titanium sleeve because somebody's decided that tungsten ball is going to fall through the fluid better. Well, the problem is that when it's coming up and that ball falls out, there is no possible way for that sleeve ever to catch it. So it always has to go down. So you're going to get these slow cycles or no arrival, and then you get a fast arrival because it happens to be partway through, or something will be very inconsistent. When you see that, you need to double check your weight ratio. And I find a lot of plungers out there that the weight ratio is like, nobody even talks about this anymore, and it's kind of forgotten. But those weight ratios are critical to making these things perform properly. So if you're getting a lot of inconsistent runs, increase the weight ratio differential. Heavier sleeve, lighter ball. Okay. Now, again, as your gas rate drops closer to that 60% of wellhead critical rate, and that's kind of my 60% or greater is kind of a no-brainer, where you should be able to run a 2-piece plunger. Typically, that's, we can get them lower than that. You might be able to get them down, depending on the pressures and the depths, down to 40-45% of wellhead critical. But that's pretty consistent, where I would say this is a pretty easy, this or above is a pretty easy application for most 2-piece plungers. Now, if the ball is too light, typically what results is the ball is either not going to fall against the flow, so your sleeve and ball come up, it knocks the ball off, and the ball just sits there and rattles in the tubing, and it's not going to fall because it might be too heavy, the flow might be too high and the ball is too light. So we would have to consider maybe a slightly different combination, or the ball is falling so slow that you have to have a really long afterflow. in order for it to get down to the bottom, or it gets in the fluid and will fall. And then what will happen is you start getting real inconsistent cycles as well. You'll probably get a fast run, then you may get a slow run, and it depends. Like if the ball gets down into some fluid that's strung up into the tubing, the sleeve will catch it halfway up the hole, or it's not getting all the way down to bottom. So a ball that's too light may create some issues, and he might give you some inconsistent runs, which may look similar in what's going on. But there's two things happening. One, the ball isn't getting down there, and the other one, the ball's not staying with the plunger on the way up, and it's having to run back down. So those are a couple of different things that'll happen. So if you're having these problems, you can look at your weight ratios and see what you can do about adjusting that, and it might smooth out the operation. So on a low flow rate two-piece application, as the flow rate drops below 60% of the wellhead critical rate, the ball to sleeve ratio might need to be adjusted. And really what kind of happens is this ball might fall out, and the sleeve will either have to try and catch it, or it'll run all the way to the bottom. So an example what I talked about before, you might try a lighter ball. So you might use a 9-inch titanium plunger with a zirconia ball, which is a ceramic, it's very light, or a 12-inch titanium plunger with the titanium ball. Now the lighter ball again just means that the ball and sleeve separation will be less. It won't fall apart. And every time you get this, like if you get into a poor condition where that plunger is just kind of sitting there floating, this ball and sleeve will chatter, and it'll let gas through, and it'll let liquid drop out the bottom. And that plunger will actually kind of step through the column of fluid that's above it until it gets under enough fluid that it can, it actually can continue to lift it. Sometimes that's a good thing, but most times that just makes it very inefficient. You get inefficient runs, so you just have to look at how you adjust your ball to sleeve weight ratio. So you get this chatter separation in there. The other style of ball and sleeve is one where there actually was a ball, and then they have something like a snap ring, or they may have magnets or different things near that actually hold the ball in, mechanically hold the ball into the plunger. And the weight ratio is not as important, but my experience has been over this time is the snap rings and that they wear out very quickly, because you can remember you can do 200 300 cycles a day with this plunger, so these snap rings and stuff get worn very quickly. So within a few weeks it's no longer holding the ball into the plunger, and typically then you start getting a lot of inconsistent runs. And the only reason why most of these plungers, I think, originally were designed was it was a way to get away from the patents that Pacemaker had, which was that weight ratio that we were talking about was part of them. So they did this to go around the weight ratio. Now there is some benefits to this, is when you could run a much heavier ball than you normally would with a Pacemaker style, and if you had really high fluid volumes, you might be able to get that ball to fall where the other one would have more difficulty. But typically my preferred method is always using the Pacemaker style without the snap rings, but that's just me. If it works for you, it works for you. Got to use what you like. But then you've got to inspect these snap rings, these locks, and make sure. But if you have a really out of whack weight ratio, you're going to find that they just become inconsistent and very difficult to operate. So that's one of the things we got to look at. So unlike the Pacemaker, the ball and sleeve plunger can have that much heavier ball than the sleeve ratio because of the locking ring. And again, like I said, it's still a good practice to try and stay within that 9-to-1 ratio if you can. And that's because a retainer ring, typically they fail, and you get a short life out of the plunger if you don't. And one of the biggest mistakes I see is people make is expecting the plunger to travel at or near the same time as a conventional plunger does. And you got to remember that a two-piece plunger, you never want to drop it without flow. You want that plunger to come out of the lubricator and then very quickly bring the flow on, whether it's a restricted flow or full flow or however. But if you drop those plungers without flow, they can get such high speeds. And I see a lot of people doing that because they want to get that plunger down there and bring the well back on, and they drive that plunger down there. And if you're doing that, you're going to eventually beat up and destroy your bottom hole spring, probably damage plungers, and it's just not really the way they were designed. These were designed to run continuously with very, very short off time. So you need to figure out how to get your weight ratios, the heavier the plunger, the heavier ball, whatever you need to work in your well. But you also got to remember that you have to wait for that plunger to get down there. And if you have a properly weighted ball and sleeve, that plunger will probably fall somewhere around that 1,800 feet per minute. So that's 500 to 600 meters per minute. So if I've got a 2,000 meter well, it's going to take me 4 or 5 minutes to get the plunger down there. It might even be a little longer than that, but that should be the expectation. So if a conventional plunger would normally take me 10 minutes to go from the bottom hole spring to surface, so that's the numbers, 10 minutes, I've also got to realize that there's 4 minutes of fall time or 5 minutes of fall time. So my plunger when I open up the well, or I drop the plunger, then I open up the well and it's still falling, there's another 4 or 5 minutes, hits the bottom, and then it comes back in that 10 minutes. It's going to be 15 or 16 or 17 minutes or something. It's going to be a normal plunger arrival time. It doesn't mean it's doing it wrong. It actually means that's what it needs. So unlike a conventional plunger where you have delay time, that's the time you let the well flow, part of the delay time is actually in the plunger fall time, or becomes the open time, because the plunger has been released. It goes into open, or a plunger wait time, or plunger arrival time, or whatever you want to call it. So you have to include that. But I see a lot of people say, "Oh, we want that plunger up in 10 minutes because that's what a conventional." But that's not what you want. You need to include that fall time. And if you don't do that, you're never going to really optimize a two-piece plunger the way it should be optimized, which is if you're doing that where you're letting that plunger fall in the flow consistently, you could make, if I can do a cycle in 15 minutes from top to bottom and back to top again, and I can do 4 trips an hour, I can make a ton. So that 4 trips an hour, that's 80. What is that? 96 cycles a day. I can make that plunger run, or even faster sometimes. So you can get a tremendous amount of cycles out of these, and they'll lift a tremendous amount of fluid, but you have to be patient. Now, a two-piece requires a flow velocity, and it's not pressure buildup like I mentioned. And because we're using tube velocity, we can correspond this kind of back to critical rate. Now, I always use, again, a 60% of wellhead critical rate as my kind of go, no-go. If I'm less than 60%, I'll usually look at, instead of a two-piece, I'll move towards a free cycle type plunger where the valve is built into the plunger. And typically, even as high as 75%. The ball and sleeve I usually use on the highest flowing wells. So 75 to 120, 25% of wellhead critical is where I would run that two-piece plunger. And like our Pro Cycle, for example, but a free cycle plunger, which has the valve built into it, we would run that somewhere between 60 or 50% of wellhead critical, all the way up to that 110% of wellhead critical. And then we would run our equalizer, which has an actual valve and a trip built right into it. It doesn't have an external trip rod. That would be somewhere from say 40% of wellhead critical to 70% of wellhead critical. Typically, you need a fall time for that, so we drop that type of plunger, you would have no flow. But anytime you're doing a pacemaker or a two-piece ball and sleeve, you need to flow when that plunger is falling to maximize the life and the effectiveness of that system. And remember, we're not building up any pressure, so 100% of the energy that drives that plunger back up has to come from the formation. So you're not building any energy, not shutting the well in. So that's why we use critical rate versus GLR and build up and And when we get into doing things like load factors and things like that, that's not the way. We just need to know that we got enough gas to continuously drive that plunger up and down with the fluid that it's producing. Operational rules of thumb: close time. Only what is required to ensure the plunger sleeve comes off the separator rod, drops out of the lubricator, and into the tubing string. Again, typically that's somewhere between 5 and 30 seconds. It depends on what the valve reaction time is, and some valves can take a minute to actually close, if they're being run by SCADA. So you have to understand that. But you just want that plunger to get out, and you want to open it again as soon as possible, because most of your wells, within 2 minutes, this plunger is going to be at bottom, and it's going to hammer whatever equipment's downhole. And again, we should never let the sleeve hit the bottom hole spring without the well flowing, or you're going to have a lot of damage. There's a lot of kinetic energy, and even that very light plunger traveling at 4 or 5 or 6,000 feet per minute, it can do some damage. Open time: 1.5 times plunger target time. So remember I was saying how typically we would say conventional plunger time is going to be based on 750, 800 feet per minute or 250 meters per minute, something like that, and we'd come up with a number. But because we got to include that fall time, we got to figure out what that is. In this time, you might, I say example plunger is 7 minutes. Well, a free cycle, I'm seeing a 2-piece plunger is going to be 7 minutes based on what a conventional plunger would normally do, plus the fall time, which might be another 3 or 4 minutes. So that's going to be 11 or say 12 minutes. And that means I'm going to have an open time of not 10 minutes and 30 seconds like I show here for a conventional, but I would probably have an open time of something like, let's see, so we got, 12 minutes and 6, so 18 minutes. My open time would be 18 to 20 minutes. That's what I would wait for the plunger to show up. And again, note on shallower wells that are less than 1,000 meters, this time might be increased 2 times target time. It just depends on how fast that plunger is cycling. Backup or plunger fall time. Backup time can be pretty good when it's with a 2-piece plunger, but a good start, and basically what you do there is your backup time with a 2-piece plunger should always be set up as if it was a conventional plunger. So if our normal fall time in a conventional plunger was, we're just going to say 150 feet per minute is what our fall rate is we're going to use, or 50 meters, we'll just use 50 meters, and the well is 2,000 meters deep. That means I need to have 40 minutes of off time. So if the plunger doesn't show up, the 2-piece plunger doesn't show up, and here's another thing, don't have it so it fails on one miss. A lot of these 2-piece plungers, you have to let them, sometimes they do funny things, and they do miss. So maybe you say, well, if I miss not 1 time, but if I miss 3 times, then go into backup, or maybe it's 2 times, and then it'll go into this backup, where it actually shuts in like a closed plunger, or a conventional plunger. It lets it go to bottom. It'll be shut in for 40 minutes because say it's a 2,000 meter well, and then we would bring it back on and let it, if the plunger showed up, then we would go through back into the normal short close time of a few seconds to let the plunger come out. And that's typically how I use a backup or a plunger fall time or fail time if it doesn't show up. Now, you can always fine tune that as you're working on it, but it's a great place to start because you don't know if that plunger is sitting at the wellhead or just below the wellhead or where it is, and did it knock the ball out or didn't, and if it's got the proper weight ratio or if it's got the little pin or the snap ring in it. If you only shut it in for a minute or two, that plunger is going to drop part way down and come zipping back up and smack the lubricator. So typically what we want to do is give it enough time to get to bottom as if it was together with the ball and sleeve. Minimum delay. This is very important for the Pacemaker style plunger, the 2-piece, because because the ball falls slower than the sleeve. If the ball and sleeve comes up, knocks the ball out, and 10 seconds later we shut the well in, that sleeve is going to go down and catch the ball right away, and it's going to come back up, and it's just going to repeat it, so it's never going to get down there. Now, based on that 9-to-1 weight ratio, I found that 1 minute for every 1,000 feet in depth, or about 1 minute for every 330 meters in depth, is a pretty good or 305 meters per depth is a pretty good wait time. It almost always ensures there's separation that the sleeve won't catch the ball. Okay, even within that ratio. Now, if I was to run, say, again, a much heavier sleeve or a much lighter ball than that 9-to-1 ratio, and I made it 12-to-1, I may have to extend that out a little bit because that sleeve is going to fall much faster. So instead of 1 minute every 1,000 feet, I might go 2 minutes every 1,000 feet. So if I got a 10,000 foot well, I might need a minimum delay time of 20 minutes if I was running a 12-inch titanium plunger with a titanium ball. Whereas if I was running a 9-inch titanium sleeve and a ball, I might be able to get away with only 10 minutes instead of 20 minutes or somewhere in there. You always got to fine tune, but you have to start somewhere, and you start with safe numbers and then you optimize from there. So target time. Again, we talked about this earlier. The total plunger time taking to travel from surface to bottom, hole spring, back to surface. And it's sometimes hard to identify, well, how long does it take that plunger to get down there, and what's a good rate, or what's a good time. And I find a lot of these wells, they might take 30 minutes or 25 minutes to actually get that plunger down and back up, and that's fine. It works perfect. You just come up, you just run your minimum delay time, and you cycle it again. So all of your afterflow is done during the plunger fall cycle, versus like a true, what we call delay on the afterflow time on your control system. So it's really important that when you're trying to optimize these wells, so how do you identify the time it takes to fall? One of the things I've always been able to see, and it's maybe a little harder in some of these big horizontal wells where you're injecting gas like a gapple, but if you watch your flow rate, we had a chart, you could actually see the plunger hit the bottom, and you would actually see the flow just dip down a little bit when it got down there. And then you would start timing, and you say, okay, well, based on my flow rate and stuff, it should take it 10 minutes to show up in. Boom, it shows up in 10 minutes, and okay, well, that's what I saw. If it's SCADA and you can, do high intensity polling when you after you drop the plunger, just to get an idea, you can probably catch and see the drop in pressure, the drop in flow rate when that plunger hits the bottom and the ball and sleeve get together. Because remember, when it's just falling, there's no seal. It's not carrying any of the weight of the liquids or anything that's in the tubing. So, but once it hits that bottom and that ball slides into the plunger, any fluid weight that's above that plunger is transferred to that plunger, and it'll instantly create a restriction, or a hole start to hold back on the well, is that weight starts to increase as it's moving up. So you'll see a very clear drop in production. It might be, 30, 40, 50, 100 MCF. It might not be very much at all, but you almost always can see it if you're watching for it. And once you have those times, it'll be pretty consistent after that. So sometimes you just got to stand there for 1 or 2 cycles, make sure it's 8 minutes, it's 9 minutes, and then you go from there. So that's a good way to get the fall time. If you're forcing the plunger to cycle because you're leaving it closed to drive it down there quickly and to bring the well back on, you're really just beating up the plunger, and you're not going to be operating it in a nice, smooth manner. You can get away with practically no off time by just doing a few of these steps, okay? Now, you must cycle this plunger with fluid. I'm telling you, if you want to wreck a bottom hole spring, just cycle one of these plungers without a bunch of fluid in it, or with no fluid in it, and they will beat it to death, and you'll be in there trying to fish it out. And most of the time, those bottom hole springs come out with the RIG pulling tool. Basically, they come out with the tubing, not with a wire line. It'll pound those fish snacks, and you can have the titanium top or the 17-4, whatever. They're just a wrecking ball if you're not running them properly. And that's why a lot of people stopped using them, because they weren't running them properly, and they were getting these very expensive repair and maintenance costs. And it was all about how they're being run. It's not the plunger, it's not the design, it's the operation that creates these issues. So the other thing is, you got to ensure it's lifting some fluid. The only way to ensure this is to take the time and listen to the plunger cycle. You need to stand by the wellhead. You can't optimize plungers strictly from the computer screen. You got to go out and stand beside the wellhead once in a while. I also recommend that every 3 months a plunger, and quite honestly, I prefer on a 2-piece plunger, you should be pulling them out once a month to quickly inspect them, at least for the first replacement cycle. So you might pull it out every month for the first 6 months or whatever, and see how the wear is going and look for unusual damage or whatever. And then you might be able to extend that to 3 months or 4 months or something like that once you get kind of a base. The 2-piece plunger always travels to the bottom of the well with a greater velocity that can rise to surface. If these things are falling, they can fall at such huge velocities. Again, 6,000 feet per minute. I have tracked them, and it's amazing the kinetic energy that you can create with these to damage stuff. If you're damaging the top lubricator spring because you're not lifting fluid each cycle, you're most likely damaging, I almost guarantee you, 100%, you're damaging the bottom hole assembly as well. So it's a lot more expensive to fix bottom hole than it is that little spring or at surface. So keep that in mind. You also need to remember to know the 2 types of plungers you're using. Again, if you've got the retainer ring, you may not need the weight ratio to make it work, but once that retainer ring is either stretched or failed, it's not going to work properly. So you should understand the type of sleeve and ball system you're being sold, whether it's the Pacemaker or the ball and sleeve. You should never drop, you have to understand the importance of the weight ratios between the ball and sleeve. Never drop the sleeve with the well in a closed position long enough for it to hit the bottom hole spring. Fluid volumes are what dictate ball and sleeve weight. I see guys, put these great big heavy sleeves and balls because they got high flow rates but very low fluid, and those things are wrecking balls. Again, they will beat the heck out of everything. So you're better to, if you have very low fluid, I would stay away from a 2-piece ball and sleeve. I would look at free cycles or other plungers that fall a little bit easier, slower. Plunger length, it's important. Plunger length increases efficiency, but with a 2-piece plunger, because we can make so many cycles, efficiency is not really an issue. So what if I leave a little more fluid behind per cycle? Well, I'm going to make another cycle in 10 minutes, and I'm always going to be able to keep ahead of it. Where if I was in a conventional plunger, efficiency is extremely important, because I make 1 cycle an hour, and everything I leave back there is going to impact my production for that whole entire hour. Well, if I leave a little bit behind with a 2-piece, 10 minutes later I'm down there and I've got it out again. So you can run a less efficient plunger, a smaller, lighter plunger, and you combat the inefficiency of that short plunger by more cycles, which you can't do with a conventional type plunger with off time. And it's always good practice to watch the well production while the plunger is falling. And again, like I just talked about, you can see that plunger hit the bottom typically, and give you some good ideas on what your proper cycle time should be, top, bottom, back to top again. Anyways, that's my conversation about the 2-piece plungers. Just some basic thoughts and ideas. If you have any questions, feel free to send me an email or comment on this video. You can reach me at cmason@kaizenws.com. That's CMASON@KAIZENWS.com. And thanks for spending the time. Have a great day, and hope your summer or whatever time of year you're watching this is going great. And take care.